Hi everyone, my name is Tristan Dabet. I am a postdoc at Stanford University, and I'm going to give you now an overview of our work on stimulating biogeochemical cycling in an alluvial aquifer. So in this work, our objective was to investigate how small-scale heterogeneities may influence at a larger scale an aquifer. So heterogeneities in terms of biogeochemistry and also in terms of hydrologic properties. For this, we developed a reactive transport model of a series of column experiments that are represented here, where lenses of fine-grained organic carbon-enriched sediments are embedded in a coarser-grained aquifer material. This model was developed and implemented in CrunchFlow, and you have here a description of the model itself. Our main objective was really to determine what are the main biogeochemical fluxes and reactions taking place in this system. So we designed 3 scenarios of increasing complexity that are in particular trying to pinpoint what is the main, what is the role of microbial activity occurring inside the lenses and inside the surrounding sand. At the center of the poster, you will find the calibration results for the aqueous phase. So inside the lenses on the right here, and inside the sand here on the left. And at the bottom of this center part, you will find the calibration results for the solid phase. There are 2 main results from this work. The first one is that the reducing conditions that are initially present only inside the lenses propagate into the surrounding aquifer material over the course of a few weeks. For instance, if you are looking at machinawite, so machinawite, which is an iron sulfide mineral, so completely reduced mineral, and if you are looking here on this graph at the amount of machinawite present in the sand at the end of the experiment, you can see there is quite a bit of machinawite here in red, present quite far away from these reducing lenses. So you really have like a development of a halo of reducing condition in the vicinity of those fine-grained organic carbon-rich lenses. And the second interesting finding of this work is that this halo of reducing condition do not result from a direct export of already reduced species from the lenses, so for instance sulfide. This reducing halo corresponds to a secondary reaction zone, stimulated by organic carbon exported from the lenses. And this organic carbon can be exported either as dissolved organic carbon, which would be here model 2, or as colloidal organic carbon, which would be here model 3. And on the top right part here, you have a synthesis of the main biogeochemical fluxes and reaction at work in the system, where you can see here the mobilization of organic carbon from the lenses that then diffuses out into the surrounding sand and create this halo, this secondary reduction zone characterized by a cascade of reduction reaction. And in terms of consequences and environmental implications, the first one is that a lot of reactivity in this kind of system is mitigated by mineral precipitation, and as such there is not a lot of information to be found in the aqueous phase. To really be able to understand, characterize, and be able to predict what happened in this kind of system, you need either solid phase measurement or potentially colloidal phase measurement. Another important implication is that this reducing halo represents a large inventory of reduced species. Like if you are looking here at model 3, which is our best fitting model, this inventory is nearly equal to the initial inventory of reduced species present inside the sand. So in this kind of systems, you are looking at the potential remobilization of a large amount of potentially contaminants that are stored in the aquifer and so are very vulnerable to a chance of hydrologic changes coming, for instance, from snowmelt. And finally here you have a summary of the main conclusion of this work. I hope that this presentation was interesting for you, and I will be of course available for any questions that you might have.